Now I have the whole thing. So I'm taping two just in case something goes wrong there. I have it.
I'll tape it too, just as a backup.
So we have Pranav, Sean, Philip. We have two Pranavs? No, just one Pranav. And Pranati. Okay. Gaurav Desale.
Hi.
Hi.
Igor. Hey. We're gonna wait for another tenant, as I was telling you. Okay. Yeah.
How are we doing? Let's go for.
Should we? Are you guys ready?
Yep.
No. Okay, so can you share your screen, Phil? I think our face.
Okay, now I can see you.
And I'll start recording.
Okay. Am I hearing Philip?
Oh, are we starting?
Oh yeah, and another thing, if you guys have any questions, please keep them in mind or something, and then ask them towards the end of the presentation. Or you can always type it down in the chat. So there's a chat icon.
Oh, where is it? Where is it?
So at the where the share screen icon is.
Yeah.
Oh,
there's a chat there. Okay, got it.
So that opens up the chat.
So I'm gonna keep this on.
Okay, so should I start now?
Yeah.
Okay. So, hi, I'm Philip, and I'll be doing my presentation on T-Tauri stars. So, to begin with, T-Tauri stars are named after the T-Tauri star in the constellation Taurus. T-Tauri was discovered in the 1800s and is a variable star about 460 light years away. And being a variable star, the magnitude fluctuates between 9.3 to 14. It's pretty young, only being about 1 million years old. And also, as you can see in the picture, the T-Tauri star is near the cloud NGC 1555. The T-Tauri being in the center and the cloud surrounding it. And also the cloud is being illuminated by T-Tauri, and since T-Tauri's brightness fluctuates, then the cloud's brightness also fluctuates. So T-Tauri stars are of course named after T-Tauri, and they share the same characteristics of it. T-Tauri stars are pre-main sequence stars that are contracted to the main sequence, and they're usually found near molecular clouds and can be identified by their variation in apparent magnitude. The variation magnitude could be intrinsic or extrinsic. Intrinsic meaning that the star's luminosity changes because of the star periodically swelling or shrinking. And extrinsic means that the star's changes in brightness are caused by something physically blocking the light reaching Earth. So usually T-Tauri stars are less than 3 solar masses, and they're pretty young, about between 100,000 to 100 million years old. T-Tauri stars are the youngest visible FJ, K, and M stars, and since they're on the cooler side of the stars, then their central temperatures are too low for hydrogen fusion, so they're powered by gravitational energy that's released as the stars contract. Also, they can be powered by lithium burning, which I'll talk a little bit more about later in the presentation. Are there any questions right now?
Wait, could you explain the intrinsic extrinsic thing again?
Okay. So intrinsic or variable stars are stars that vary in inherent magnitude. And then there's two types, intrinsic and extrinsic. Intrinsic means that the star's luminosity changes because the star is swelling or shrinking, and that affects the light. And then
Okay, keep going.
And then extrinsic means that the star's brightness changes because something's blocking the light reaching Earth.
Okay. All right. Thanks.
So like I think like I only took like the free version of this this platform thing. So we might switch to Mr. Batalha's meeting. So when should we do that?
Oh, he still have 8 minutes.
8 minutes, yeah.
Yeah, so
should we-
let's say
an hour
5
later?
minutes, and then meanwhile, I'm gonna text the meeting ID from my computer.
Okay. So should we just keep going?
Yeah, just keep going.
Okay. Did I go over this slide already?
Yeah.
Okay. So
I have a question.
Oh yeah.
Yeah, sorry, but what does FJKM stand for?
Also, in this chart, if you ignore the LT part
Mhm.
at the end, this is the scale of heat that the star produces. So O is the hottest stars and M is the coolest stars.
Okay.
And if you remember, O stars are usually like they're really blue stars because blue is also always associated with really hot temperatures, and M stars are usually red stars, and those are the coolest types of stars.
You
And
you,
you
could
might
see,
actually see that with red dwarfs. In fact, they're actually like a lot of like we've been discovering a lot of exoplanets orbiting around red dwarf stars, mostly because most M stars are also very small, and that means they kind of like generate a very low temperature, and so they have a very red color. So it's kind of easier for us to spot exoplanets orbiting M-type stars.
you could also change those letters to temperature, like 50,000 in O, and then go down to about 3,000 Kelvin.
Our star is a G-type star, so it's right in the middle, or in a way, ish.
So T-Tauri stars usually take about 1 to 12 days to fully rotate compared to a whole 30 days for the sun. T-Tauri stars most T-Tauri stars have large areas of star spot coverage, or for our sun, it's sunspots. And they have very strong X-ray and radio emissions, and they're about 1,000 times stronger than the sun. They can also have extremely powerful stellar winds or high-velocity bipolar jets. So in T-Tauri stars, there's a process called lithium burning, which is basically the depletion of lithium in a star, and it creates a lot of energy. Like I said before, T-Tauri stars aren't hot enough to use hydrogen bonding, so they end up using lithium burning. Rapid rotation tends to increase lithium burning, and T-Tauri stars tend to speed up their rotation as they age. So lithium burning, like towards the end stages of the T-Tauri star, lithium burning becomes one of the main sources of energy for it.
If you consider T-Tauri stars or low mass stars, they have a fantastic convective system, and this convection brings down material from from the surface all the way down to the core, where the temperature, I mean, you don't have fusion reactions at that stage, but you do have a core with high temperature. So lithium is brought from the surface down to the core or to regions close to the core where the temperature is high, and then lithium is depleted. So eventually, after, and you can calculate that after several millions of years or hundreds of thousands of years, depending on which stage we are looking at, the lithium in the surface is depleted. So you can probe young stars by the depth of lithium line. So the sun has lithium, but the line is just almost nothing. And in fact, you can use those features in order to probe the stellar age for the sun. But when you look at the lithium line in T Tauri stars, it's something phenomenal. It's deep and it's broad and it's quite significant. And then as the star age, that line falls down. And when they start reach the main sequence, then the lithium is pretty much like the sun.
So there are two main types of T Tauri stars. There's the classical T Tauri stars and the weak-lined T Tauri stars. So classical T Tauri stars are T Tauri stars that have extensive disk and strong emission lines. And then weak-lined T Tauri stars have a very weak or even non-existent disk. Weak-lined T Tauri stars are particularly interesting because astronomers and scientists are able to look at the early stages of stellar evolution without any material blocking the view of the star. Yeah, that's pretty much it for my presentation. So
Very good, very good. Okay. Just in time. Look at that, 2 minutes to go.
So, do you guys have any questions or anything like that?
Are there any questions?
Okay, so should we switch over to your?
Yeah, let's do that. These are the numbers of my meeting, so I'm gonna get out. I mean, don't get out of there yet. I will, and then I
make sure. Stop the recording too.
What?
You should stop the recording so that way you don't lose.
Okay. Well, I'll keep recording. But yeah, and you should save it now. Your part. Okay. I'm gonna get out and go back. Hello. Are we all there?
Yeah.
Okay, good. And I'm still taping. Where is Sean and Philip?
They're probably at the own meeting.
Oh, Thomas is there. Hi, Thomas. Pranav is there. Can you guys hear me?
Yep.
Okay.
Again.
Okay, I think everybody's there. Thomas, I apologize. I completely blew it. We changed meeting numbers, and I was in the middle of baking a smashed potatoes, and I forgot. And so the meeting we had previously ended in 10 minutes because we start late, and now we are continuing the meeting here in the meeting ID you had it. So yeah. So this is Thomas Hemingway. He's from Evergreen Valley College, and he's joining the group. And Phillips was made a general description of T-Tauri stars, and we were going to start a debate on it. But I can't see Philip in there. I can see Pranav.
Oh, I'm here.
Oh, Philip's there. Okay, got it. And Sean, is Sean there too? I can see Sean. Sean there. Okay, I just text the meeting ID to Sean. He might be saving the tape. Oh, Sean's there. Okay, very good. I think we are all here, right? Are we missing anyone? Are we all here? Are we all good?
Yep.
Okay. I would like to go over the source of variability. Philip, in the beginning of your talk, you mentioned the extrinsic and intrinsic variability. The intrinsic one associated with the pulsation, right? And the extrinsic one, if you do have some material that passes in front of the star, and then you have some variability, like if you have a planet, or if you have a companion, or if you have some blob, then that is going to affect your photometry. T-Tauri, yes?
Philip, can you share your screen?
Oh, sure.
Oh yeah, the screen is all black. Okay. There you go. So if you go to, I think the third slide or fourth slide. There you go. Yeah, there you go. So the intrinsic is when the star itself changes its luminosity because of pulsation. And then you can see this type of phenomena happening in our Lyra or Cepheid, or any star that goes or undergo a change in the physical volume of it. And the extrinsic is when you have some external factor affecting the star luminosity. I mean, T-Tauri star is a system that consists of a star, but also has a circumstellar disk. In addition to that, you have these magnetic fields that channel material to specific regions in the stellar surface. So, because of magnetism, T-Tauri stars have spots, like the sunspots, but you have those in this type of stars that are enhanced because the magnetism is more intense. And in addition to these sunspots, you also have these hot spots. They are the result of controlled accretion onto high and low latitude regions. So as the star rotates, these spots produce variability in the stellar luminosity. So you have a fluctuation in the light curve, and then you can track that and then you can in fact, you can use that to establish stellar rotation rates. So how long it takes the star to complete one turn around its axis. So there is another source of variability in T-Tauri stars, and that is caused by the disk itself. So the disk, as you can see in this nice picture here, for instance, this star itself is kind of blocked from view because you have some kind of a fuzzy luminosity coming out of that accretion region. I mean, not in the disk itself, but if you look at the center part, there is a haze there. It's kind of a fuzzy. And this is trying to picture emission that comes from the accretion that is being guided by magnetic fields. So this is another possible source of luminosity. So when the accretion, which means when the inflow of gas to the star increases, so you have more of this shock going on in the stellar surface, so increase the number or this area or the luminosity of the spot itself where collision is taking place. So increase the luminosity in there, and then you can correlate the increasing luminosity of the stars with the increasing accretion rate. For instance, the disk is not uniform. This is not a real picture, right? It's kind of an image rendering what's going on. But so certainly the distribution of gas in the disk is not uniform. So sometimes you might have more of that blob following the star, and then you're gonna increase the shock on the stellar surface, so increase the temperature, increase the flux, and then increase the luminosity. So luminosity is therefore correlated to the accretion rate. Is that okay?
Oh yeah, Mr. Bataha.
Yeah.
You said that you would last week. You said that you would show us some data.
Yeah. I don't have the data because you guys are way ahead of me with Python. I'm still kind of in the kindergarten, and I can't get my data. But I got two papers here I would like to show you. So the other possible source of variability is what Philip is indicating as extrinsic. So these stars, they have cometary material around, like comets, blobs of comets. They are in the process of formation. And sometimes these blobs with big coma passes in front of the star, and then you have a dimming of stellar luminosity. Since these blobs are formed very far away, you don't measure them again. It's not something cyclic that you can use that to kind of a probe cometary material. This was first indicated in Herbig-Eb stars, these big blobs, and they were suggested as cometary material. So you have all you want, basically. Okay. Now let me show you, I said I was going to bring a couple of materials. Let me share a screen here. For me to share a screen, Philip has to stop sharing his screen. There you go. So let me look and see what I got. Let me go back here.
Wait, Mr. Bataha, is this being recorded?
I'm still recording.
Okay, good.
Yeah. So this paper is one star. It's called TW Hydra. It's a T-Tauri star, and in this paper, what we did, we took a continuum. This is pretty much spectroscopy, but it's a spectroscopy of low resolution. So in this plot, this is what I would like to show you. So you have this wavelength, 3,500 angstrom to about 5,000 angstrom. So it's pretty much in the blue region. And these dark lines you see here is pretty much stellar flux. And so you have stellar flux measured in logarithmic scale. So you have 10 to minus 9 ergs per centimeter square per second. That's the kind of a classical unit used on these stars. And so what I'm doing here is following this particular star, this TW Hydra. So what's interesting with respect to this star is, see this region right here? This is called a Balmer jump, the Balmer jump. So you have the continuum that goes all the way to the point that you have a Balmer continuum transition, and then you have a jump to even smaller wavelength. Now this jump, as you can look in the spectra, the size of it changes depending on the day of your observation. This is the day right here, and the intensity of the line. So Philip was mentioning classical T-Tauri stars as the one that have strong lines, and weak T-Tauri stars as the one that doesn't have a strong lines. So what he meant was emission lines. So classical T-Tauri stars like TW Hydra, if you look at H alpha, which is the hydrogen line, and H beta, which is also a hydrogen line, these lines show a heck of an emission. And in the very early beginning of this research, astronomers thought in the 80s and 70s, they thought this emission was being produced in the chromosphere. And now we know it's not. It can't be. It has to be formed in these accretion funnels outside the star. And then this jump, as you can see, changes depend on where and when you observe. And then you can use that to model the accretion flow. So we did that in the continuum part of the spectrum. And pretty much it's a small region. It's just in the blue region. And you have nice emission lines in the hydrogen, and then you can see how this emission change depending on the Balmer continuum change as well.
So what exactly do the emission lines represent, or what do they suggest?
Okay, that is another paper. So let me show you this other paper here. Can you see this one? These lines? Or it's not appearing? Is it appearing there?
Yeah.
Yeah. So these are hydrogen lines. So this is H alpha, which is the first transition from the level n equal 3 to n equal 2. That's the Balmer alpha. And then you have the Balmer beta, which is the level number 4 to level number 2, and so on and so on. This is helium line. This is the sodium lines. So these major emission, this is a heck of emission. If you look at the sun or any main sequence star, they don't show this strong emission. And that's why astronomers thought in the 80s that was being produced by chromosphere, because chromosphere activity can enhance these lines. But there is some problem here. The problem is, if you look specifically, for instance, this helium line, you have a very narrow and symmetric component, and you have a broad line that is not symmetric. In fact, it's kind of off as far as symmetry is concerned. And when you look at hydrogen, look at all these kinks, and it's completely lacking symmetry in there. So what we did in a following paper was to analyze in details a bunch of spectra of this star. Let me show you if I have there you go. So this is H alpha with more detail. And what we did, instead of plotting the line with respect to wavelength, we are plotting with respect to velocity. So how can we do that? So we know Doppler effect. Doppler effect is an effect that relates shifting frequency to features that are formed as the gas either approach you, observer, or move away from you. And so you can, for instance, at zero velocity, it means we are pretty much looking at the rest frame. So as if you were in front of the star and you are pretty much, stationary with respect to the star. And the way we find this 0 point is by observing several photospheric lines and then make a correction so that all the photospheric lines are at rest frame, and so hydrogen line, the H alpha line. And then, so this point here represents a part of the hydrogen line that's immovable or come out of a gas that is immovable with respect to the star. And all these other components come from gas or cells of gas that have a projected velocity given. And this is 200 kilometers per second. Negative means it's going away from you, and the positive part means it's gas that is going towards you. So we have a blue shifted part of the spectrum and red shifted. So when you look at these kinks, you are kind of estimate, okay, this kink at about, let's say, 100 kilometers per second is blue shift, which might indicate a gas that is going away from you. In other words, it's a gas that is following onto the star. And that's what we did. We observed several of these stars. We had several observations, consecutive observations, and then we analyzed if certain part of the spectra was showing any sort of variability based on the stellar rotation, and if that particular gas emission or cell of gas was correlating with the same position in other lines, like helium line or sodium line or calcium lines. It's a kind of a not tedious work, but you have to do a lot of analysis in several lines and do matrix correlations and decomposing line profile like we did here. We decompose this complicated profile in one that is nicely symmetric, and then we call that a region that is formed in the accretion flow, and one that is kind of a narrow but is symmetric, and then we associate that with the chromosphere. So we had two regions to explain helium line. One formed in the accretion flow, and another one is more in the chromosphere. And then we saw if this accretion flow component would show any changes as the time goes by, and then we would correlate those changes with accretion, with other factors that we observed in other spectral regions.
So I think some of us are a bit confused. Here in the graph that we're just pointing at.
Yeah.
So how exactly does velocity correspond to the intensity? So what exactly does this peak mean?
Yes.
At around the 0 mark?
So this point 1, what we do, we take the spectra, and when you do high resolution data, which is you take the light of the star and then you spread that, create a rainbow, but with a powerful technology that it spreads and that can give you details of not 1 angstrom but 0.2 angstrom in resolution. So it's a lot of detail, and then when we do that, when you spread the light, you cannot convert the stellar light to a flux, to a calibrated flux, like in the previous spectral like in this one over here. So this spectra is calibrated in flux because I have the entire energy the star is sending out to us observer. I'm collecting all of that and converting that into flux in ergs and unities that I can call that flux. When we do photometry, oops, I lost. Sorry. when we do photometry, wait a second. When we do spectroscopy, we lose that. We cannot associate what we call the continuum, which is the flat region upon which emissions or absorptions take place. We cannot convert that to flux. So what we do, we normalize. We use this word normalization. We divide that by a factor that makes the continuum equal 1. And then we study the emission with respect to that baseline, to the 1. So what you're looking at here is, well, the spectra that represents the peak of this emission line is about 2.7 times more intense than the continuum of the star itself. So that's what you're reading here. And this continuum, this peak, is resting on top of a broad line. So you can add, in fact, when we decompose these profiles, we model that. So I'm modeling this profile with two components. They are symmetric, as you can see in these with these broken lines, but they have different openings, different broadenings, and because they have different broadening, and that is related to velocity dispersion. Basically, we can discuss if that is formed in the stellar photosphere or stellar chromosphere, or in a gas that is not part of the star itself. So this broader component is not stellar. It is something exterior to the star. And this narrow component, it could be stellar. So that's what you can say based on what you observe.
Okay, so the velocity, so like on the x-axis, it's labeled velocity in kilometers per second.
Yes.
So is that supposed to mean radial velocity or velocity?
It's not radial velocity, because we are not measuring how fast the star moves in respect to us. This is the velocity of the gas. I mean, an emission line or an absorption line, when we study spectroscopy in Astro 10, for instance. So we have these absorption lines, right? So each part of the profile is formed in a specific region of the stellar atmosphere. So those broad components that are closer to continuum are formed in a region and in which the gas has more turbulence, has more scattering going on up to the point that escapes. So you can model. So this is all part of the stellar system or star disk system. And when you measure these velocities, you are measuring the velocity of the cell that produced the gas with respect to an observer that is at rest with respect to the star. So let's say if you are an observer in a spaceship observing TW Hydra, and you look at a gas that is going towards the star, is following and following on the star, you should be seeing this region right here. Whereas if there is a part of the gas that is moving towards you somehow, which means you are observing a part of the gas that is following towards the star, but this gas is beyond the star. So when it falls to the star, in fact, it goes towards you, then you are probing this region over here. Does that make sense?
Okay, so let me just say this. So what you're trying to say is that like the velocity at the bottom of the x-axis measures like how fast the gases are rotating, right?
If it is all photosphere, you can use that to measure stellar rotation, V sin I. That's correct. But the star could not be rotating. The star could be stationary. And yet you can have these big and strong lines and all anti-symmetric, depending on the gas that is overlying the star, that is either following towards the star or being pretty much expelled as a result of disk wind. So we have a strong disk wind connection in T-Tauri stars, So if you are observing the star, like in the figure, the Phillips show, you have the star with that kind of a hazy figure. If the gas that forms what, I mean, optically we think is a haze or a kind of a whitish cloud, if that cloud is moving towards us because the disk is pretty much sending particles away, we would see a strong blue shift line. So the line would be an emission, but would be blue shifted, would be some sort of a Pising, as we say, Pising profile. Whereas if the gas is falling towards the star, we would see a red shift or a feature that is more that's losing symmetry in the red part of the spectra, which is this part over here. So I don't think I have a photospheric line in this paper. Let's see if I can show. Photospheric lines are kind of boring. They are absorption. They are symmetric. They have some broadening mechanisms that you can model quite well. But I don't think I. Oh, for instance, let me show. See these lines over here? These are photospheric lines. See this little thing, this little one, this little one, these big ones. Then you have 1, 2, 3. Can you see that? All of these lines are photospheric. And if you look carefully, they are symmetric. They are kind of a composed profile because you have nearby lines in there. And if you go to a table, you can identify the transition that was responsible for producing this line. And then you can use that. You can use atomic parameters to infer stellar properties just by observing these photospheric lines. But when you see these gigantic emissions, these are not photospheric. These are something else. And the beauty of these young stars is to analyze what is exactly producing it. So if you have good data, you could do good job, good work. All right. So what these in the Kepler has so the K2, the new version of Kepler has let me stop sharing. Has a I don't know why the screen is all dark. I don't know what's going on here. But Kepler it went through in one of the missions last year. It went through Taurus Aurigae, and I know there are data on photometric data. It's not spectroscopic data, but there are photometry, very good photometry on premium sequence stars. So one of the projects I would like to propose to whoever would like to pilot this with me in the fall would be to follow some of that photometry just for fun and try to use software that is public and try to find rotation rates of these stars to compare with what's going on in the literature. If we could kind of put our hands with some professional astronomers doing the same work, you guys could collaborate with them, and I would try to get our hands on their data. So that is what I'm heading for as far as the T Tauri stars and also Herb-Gibby stars is concerned. Now I have your free meeting will end in 10 minutes. Ooh. So now I'm limited as I go. So Sean, I think that's what we have to do. You start it and then I finish. And we should start exactly at 7 o'clock. Because then we can have 30 minutes on your side and 30 minutes on mine. And then we can go all the way to 8 o'clock without problem. But I would like to this would be one of the type of projects we developed to take photometry from Kepler and then see what these people are doing and get a hands on what's going on in the field of pre-main sequence nowadays. It's exciting. It's very cool, especially now what they are doing. This paper you saw was published in the 90s, late 90s, about 2000, 2001. Yeah, 1989, no, 1999 and 2000. And what we were trying to do at that time is to find out if disk accretion was responsible for stellar fluctuation. And now it's pretty much settled. I mean, this research is kind of outdated. If we still try to do, it's cool. I have good data, but that's not what people are doing now. What people are doing now is try to find and bring about more details of the disk itself. Why? Because they want to see planets. I mean, somewhere in this nice picture Philip showed of a T-Tauri star, somewhere there in out of that cloud of circumstellar material, planets are formed. So now they want to use all the photometry they can get, plus spectroscopy they can get, and try to map planets formation. That's what people are doing now, and they are excited about it. So that would be something cool for you guys to do.
Okay. So does anyone have any questions or anything? I mean, there's a lot of material covered, so I'm pretty sure a lot of you have a lot of questions, so you should probably ask them now.
There you go. There you go. So next week is Herb Key stars. Is that what it is?
Yeah.
Okay. Who's going to do it?
I'll be presenting that topic.
Okay, wonderful. Very good. I still didn't receive the paper review from Nuria Calvet and Lee Hartman, and as soon as I get, I send it to you all.
Okay.
All right.
Okay.
Okay. See ya.
Good to see you again.
Good to see you too. Thank you, you all, and Sean, I see you tomorrow.
Right. Yeah.
Okay. All right. Bye.